Now that we've discussed the notion of inverse functions, I'm going to introduce a new topic or a new idea to that mix, and they're called exponential functions. And to introduce this, I think most of you have probably had some experience with this in an algebra course at some point in the past. So hopefully we can sort of brush through this relatively quickly and get you familiar with these ideas so that we can go forward with it. There's a notion called an exponential function. I want to consider two functions. One is f of x. This is 2 raised to the power of x, as opposed to g of x, where this is x raised to the power of 2. Now remember, in this language, in this terminology, there's the notion of the base and the exponent. Now, in the case of function f, the constant is the base, but the variable is the exponent. In the case of function g, the variable is the base, but the constant is the exponent. These are two fundamentally different types of functions. They're completely different variety of functions. They fall into different categories. This is one of a large category of functions called polynomials. And you're familiar with polynomials. You've done quite a bit of work with polynomials. This is one of a category of functions called exponential functions. Anytime the variable is in the exponent, that's an example of an exponential function. That's where the name comes from. Now, what I'm going to do is sort of sketch these two graphs. This one I'm going to do in the blue. Now, this one you should be fairly familiar with. This is the basic shape square function. I'm going to try and probably fail, I'm guessing, but to draw a reasonably accurate picture. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And now 1, 2, 3, 4, 5. So this is 5. Let's say 10, 15, 20, 25, and so on up. Now, my scale is not perfect, but you get the idea here. The reason I'm having such a tall y-axis is because we see this function gets very big very quickly. We know the function value of 1 is 1. The function value of negative 1 is 1. We know the function value of 0 is 0. 0 squared is 0. 2 maps to 4. In fact, both positive 2 and negative 2 map to 4. 3 maps to 9, 4 to 16, 5 is way up here at 25 already, 6 is off my board by now. And in this case, for this function, the negative values map to the same y-coordinate as their positive counterparts. 4 goes up to 16, 5 goes up to 25, and I'm going to probably fail here, but I'm going to draw a reasonably accurate picture here of this parabola. If the line misses the dot, just make the dots bigger, and we get the basic idea for this parabola. Now, I'm going to draw this one in this red, and let's suppose that we're going to sketch the graph of this function 2 to the x. Now, if x is 0, this is 2 raised to the 0 power. Well, any non-zero value raised to the 0 power is 1. So we get the value 0, 1. Well, 0, 1 is here. All right. If x is 1, then this is 2 to the first, which is 2. What if x is 2? Then we need 2. If x is 2, this is 2 raised to the second power. That's 4. So 1, then 2, then 4. What's 2 to the third power? Well, 2 to the third power, 8. See what's happening? You're doubling each time. 1 to 2 to 4 to 8. 2 to the fourth would be 16. 2 to the fifth would be double again. 30. So you're doubling each time. 2, 4, 8, 16, 32. All right. Well, if we were to plot those, we have 0, comma 1, 1, comma 2, 2, comma 4, 3, comma 8, and so on down this scale. So we have 1, comma 2 within the limits of my very poor picture. Then we have 2, comma 4. Well, that's the same point as it maps on that parabola. But 3 only goes up, 3 to the second power only goes up to 8. So on the blue curve, 3 goes to 9. But on the red curve, 3 only goes up to 8. But look, at 16, we have at x equals 3, 3 comma 16 is the same thing as over here, 4 squared is 16. So at 16, the graphs coincide again. Oh, my picture is very bad here. 8 is only here. All right? And then at 5, now look what happens at 5. Here, I'm on a scale here. 3 goes to 8, 4 to 16, 5. Now, where is 5 on this curve? 5 squared is 25. But 2 to the 5th power is 32. So the red curve at 5, 1, 2, 3, 4, 5, might be able to kind of sneak in a little 32 up here on the edge of my board. But look what happens at 6. 2 to the 6, you have to double again. 64. Whereas this curve only goes up to 36. 6 to the second is 36. This goes all the way up to 64. So what happens is, it's above for a while, it crosses over and is below for a while, but then it's above, and then this curve gets significantly higher than the blue curve. Now, I can't show on my scale here, but we can do this. We can compute g of, let's say, 10. Yeah, 10 to the second is 100. That's way up above, that's above my second floor probably. But f of 10 is 2 raised to the 10th power. And that, you can use a calculator if you need to, is 1024. At 10, this goes way up to 100. But the red curve at 10 goes up to 1024. That's more than 10 times higher. And it gets even bigger. At 11, we can figure that. What's 11 squared is 121. But f of 11, you double this again. 2048, it's up over 2,000, whereas at 11, this is only 121. Yeah, that's a big number. This is a huge number. And so what happens is this red curve, once it starts to move, it really goes. And in fact, to the unaided eye, it would be hard pressed to distinguish this curve from a vertical line. This red curve would almost look like a vertical line the higher up you go. Now let's consider the negatives. We know what happens with the blue curves. Negative values squared become positive. On the negative side of the picture, the red curve doesn't behave the same way. Here's x, here's 2 raised to the x. Because if x is negative 1, this is 2 raised to the negative 1 power. And we know how to do negative exponents. Negative exponents means 1 over 2 to the first. And if I have negative 2, if x is negative 2, this is 2 raised to the negative 2 power. This is 1 over 2 squared, which is 1/4. And we see a similar thing happening. 1/2, 1/4. Is it clear what negative 3 is going to become? 1/8, 1/16, and so on. And so negative 1 goes to only 1/2, then 1/8, then 1/8, then 1/16, then 1/32. So on this side of the picture, it gets very huge very quickly. On this side of the picture, it gets extremely small very quickly. And in fact, this is asymptotic. It is an asymptote, x-axis negative. And it gets very close very quickly. Let's think about what happens at negative 10. This is 2 raised to the negative 10th, which is 1 over 2 to the 10th. And we've already seen this is 1,024. This is 1 over 1,024. So at 10, you only go up 1/1000th of a unit. So this red curve is an example of an exponential curve. So now there's nothing magic about 2. We could have gone through this same argument with 3. The difference would have been 3 to the first is 3. 3 to the second is 9. 3 to the third is already up here at 27. 3 to the fourth is way up at 81 already. So as this base gets larger and larger, you get a similar behavior, but it gets even bigger, even faster. Consider this function. Consider h of x is 10 to the x. And let's consider drawing this in my purple. At 0, what's 10 to the 0? Well, 10 to anything to the 0 power, any non-zero, to the 0 power is 1. 10 to the first, when x is 1, this curve is already up here at 10. At 2, the red curve was only at 4. At 2, 10 to the second is already up at 100. You go over 2 units, you have to go way already up to 100. At 3, 10 to the third is already 1,000. This thing skyrockets. To the unaided eye, you would be hard-pressed to distinguish that from a vertical line. And then on the negative side, we have the same numbers except they are reciprocal because it's 1 over because they're negative exponents. And so this would be 1/10, 1/100th, 1/1000th. And so we have a general picture. There's nothing magic about 2. There's nothing magic about 10. We could have made the same argument with 5 to the x, or 20 to the x, or 3 to the x. In fact, we generically call this b to the x, where b is allowed to be, we use b because that's the base. This is a standard way to represent an exponential function. Either f of x is b to the x, or we may also say, and we will frequently use this notation, we may use y equals b to the x. We'll use the y notation. It's a little more user-friendly. So when we do this, this is the basic idea. This is the standard way to denote an exponential function. Now, there are certain restrictions. There are certain values of b that may not be used, certain values that we may not use as the base for an exponential. And that's when we talk about this function in more detail, that's what's going to happen with the next video.